All right, just add that there in pink, please. You only do that way of proving the derivatives if they state that you have to use the definition or first principles. Obviously, it's a much longer method, right? I'll do an example for you tomorrow. I want to get to some other stuff today. It's a much longer method, so they tend not to ask it in that way, but yeah, we do need to be prepared for if they do. This one. Yeah, some people are saying you did and others are saying you didn't. So I'll just go take a look at Mrs. Race's notes and then see. Yes. Yeah. First line definitely, yes. All right, guys, we're just going to do an example of this. Okay, so this would be the same method that we used yesterday, showing that it's continuous. If it's not continuous, you don't need to do the second one, like I said already. If it is continuous, you would have to do the second one. And for this one, you're going to check the limit from the left of the derivative of whatever that function is. And then you're going to sub in that value. Once you found the derivative, then you do the same thing with the limit from the right of that derivative and see what you get. Okay. There is something that I do want to just add here. Let's see. I hope you guys have space at the top. If a function is continuous, it's not necessarily differentiable, right? Do we understand that? Because we need to have that to be true as well. But if they're telling you, and you'll see in the second example that we're going to do, if they're telling you that a function is differentiable, then it will definitely be continuous. Does that make sense? I'm going to say it again. If a function is differentiable, then it has to be continuous, right? So sometimes they'll say that. You'll see in the second example. If they tell you that a function is differentiable, you can assume that it would have to then be continuous. So you could then actually use this equation in your working. All right. How was I going to write that? Let me just see. So it's almost like a bit of a converse statement, all right? If they're telling you that it is differentiable, then you can use the fact that it's continuous. So it might seem a bit unnecessary to write down, but I do just want us to have it. Okay, examples. Oh, sorry, have you all copied that down there at the top? Sorry. Okay, guys, I want you to do the first part of this question on your own because that is what you've practiced already. That is just proving that it's continuous. And then I'll do the second step with you guys, just in case you can't remember. But if you can remember how to do it, then you can do it, all right? But I'll just give you some time quickly to do the continuous section on your own. So you're going to do those three things. F of 2, then the limit as x, sorry, not 2, -2, my apologies. Then the limit as x tends to -2 from the left and then from the right. Okay, and if they're all equal, then it is continuous. Yes, Georgia?
What would happen if you try to differentiate something that isn't differentiable?
Well, the thing is you would get two different answers from the different sides. That's the thing. So you wouldn't know. I suppose if you didn't realize that, then you would just take the one where it's equal to -2.
So
right?
Split functions can't be differentiable.
Well, if you could have an asymptote, and then at that specific value, it also won't be differentiable.
Like a parabola would always be.
Yes.
Okay.
Mm. Mm. No, you don't have to. You can just do it all in one line, just the three of them. Okay, let's just take a look at that continuous part. Okay, so f of -2 is 3. The limit from the left, which is the limit of x squared minus 1. If you sub in -2, that will also give you 3. And then the limit from the right, because it is just 3, will also be 3. So all three of them are equal, therefore it's continuous. Yes.
Can you just write the limit of x -2 of x squared minus 1? Would you have to write both f of x equals right.
Yeah, so you're just saying you didn't do this. It should be fine as long as in your actual final line you have f of x and f of x, because that's like the definition of continuity. Okay. All right, now are we fine with this part, guys, with the continuous part?
Yeah, I would work out the other example.
Mhm.
I proved that the limit is and then I made the limit equal to that's just the long way.
I think, yes, yeah, so that's just one extra line. Are you talking about the example that we did yesterday?
Yeah, well, the example we did yesterday was split up into two,
Mm.
but I just did that in one.
That's fine. Mhm. Yeah, it's all right.
go through that. We just
Yeah, so the only reason why we did that yesterday was because the question said prove that the limit exists. But if they're just saying differentiability or continuous, then you would just, but you can also do the limit exists. It comes to the same thing. All right, guys, now we need to do the derivative from the left and the derivative from the right. So please write this down. The limit is x tends to -2 from the left of the derivative of f. Now here you would have to write derivative. Okay, Georgia, before you actually put the thing in. So let's look at, we know already that from the left, our function is x squared minus 1. So now we need to find the derivative of that function and then sub in -2. All right, so it's basically one extra step. So this is going to become the limit as x tends to -2 from the negative side, from the left. What is the derivative of x squared minus 1? 2x. And now if we sub in -2, what am I going to get? -4. Okay, now we need to do the same thing from the right. So the limit as x tends to -2 from the right of f dash x. Now guys, our function from the right is just 3. So what is the derivative of that? 0. All right, so I am going to write in here just the limit as x tends to -2 from the right of 0. And then obviously if we were to sub -2 into 0, we would still get 0. So now we see that our derivative from the left and from the right actually doesn't give us the same value. All right, it's not tending towards the same value. So is there one specific derivative at x equals -2? No. All right, so that means that at x equals -2, the function is not differentiable. So now you would have to, again, unfortunately, put in this line where you show that these two values are not equal. And now I just don't have another line at the bottom there. So I'm just going to write here, therefore, not differentiable at x equals -2. Yes.
what would
So this one is a parabola, and then it goes to a straight line graph. So if we look at this one here, where x is smaller than or equal to -2, it's x squared minus 1, which is a parabola, which is at -1, it has its turning point, y-intercept. And then this one, 3, is just y equals 3 going on from there. Yes.
In the question, does the line justify your answer actually make us add anything to proving differentiability?
Well, I suppose if they had just given you the graph, no, you would have to go through the whole thing still. Yeah, it's more if they're asking you for continuity and they've just given you a graph. Because if you have any kind of what's it called? If you have any kind of discontinuity, you can also tell that just by looking at a graph. So I suppose even if they're asking for proving whether it's differentiable and they've given you the graph and you can see that there's a gap, then you could say straight away it's not differentiable because it's not continuous. So if they're saying justify your answer, you have to do this whole thing. Yeah. All right, guys, I want to do a different type of question now where they're telling us that it is differentiable and we then need to use that. So that will be number 2. Are we done copying this down? We'll move on. Okay, now I just need to find that page. Oh, man. Is there a page lying somewhere? Am I missing it? No. Okay, I'll have to do it from the book thing. I literally just had it. Like I just looked at it. I was like, oh yeah, I'm gonna do this example stuff. Oh, it's here, guys. Oh man. Okay, sorry about that. number 2. I knew the second you guys see A and B there, you're gonna go like, oh no. Yeah, I know. I feel like you maybe had a question like this in your final exam or in some kind of test or something last year, and then it was like a problem solving thing. But then I thought you've already seen it, so it can't be problem solving anymore. So let's just do an example just to help you guys a bit in case that one didn't go very well. So guys, this is now what we wrote in pink. That's where that comes in. But if they're telling you that a function is differentiable, then we can obviously assume those two things. All right, we can assume that it is continuous and that the derivative from the left is equal to the derivative from the right. Okay. Now, guys, what I want you to notice is that they've given us the x values. Okay, so we are going to be able to sub our x values in. All right, but we have an a over there and we have a b over there. Now, guys, there are two things here. Firstly, it's continuous. Secondly, the derivatives are equal. Now, because our constant term in this first function is an a, all right, I want us to do the derivative from the left equal to the derivative from the right first, because what is the derivative of a constant term? 0. All right, so if we do that, we're effectively going to get rid of the a, which will mean that we're only going to have one variable. Okay. So that is, yeah, just a hint, just if you're looking at what you have. If you don't notice that and you do your continuous thing first, you might have to end up doing what's it called, simultaneous equations. All right, so I'm just going to write that here. That's a little hint. It is useful to look at what you've been given before you actually start working. Deriv of constant is equal to 0, therefore do derivatives first. And guys, in any case, it's probably easier to always do the derivatives first because the derivative expressions will always be simpler than the actual original expressions. All right, if they're just given in polynomial form like we have here. Okay, I'm just going to label the first bit with a little star. All right, we know that if this function is differentiable, then the limit, and it's at x equals 1, so the limit as x tends to 1 from the negative side of the derivative would have to be equal to the limit as x tends to 1 from the positive side of the derivative. Okay, that's what we're going to do first. It helps to actually write it down, okay, the kind of rule before you start doing it. Okay, so from the left, our function is x squared plus 3x plus a. Right, so what is that derivative going to be? 2x plus 3. Okay, so again, I'm just going to keep that limit there for now, just so that we can see all our steps. So the derivative is 2x plus 3. And then from the right, Our function is just bx plus 2. What is the derivative of this function? Just b. Now that's quite nice, guys, because what is this limit of b as x tends to 1? Is there an x even there? There's no x, hey? So this is just going to be equal to b. And this one, what am I going to do here to get this value? I'm going to sub in 1. So I'm going to have 2 times 1 plus 3, which is 5. So what does that tell me? B is equal to 5. There we go. Okay, and now guys, we can obviously use this b value now when we're actually solving for a in the next one. So I'm just going to write in pink here underneath that this equation is actually 5x plus 2. You don't have to write it there, you can just kind of remember it. Okay, so now we just still need to find a. Now we're going to use the fact that this function is continuous, right? Because they've told us that it's differentiable, so therefore it has to be continuous. So I'm just going to write the next bit. Now, if a function is continuous, or if this function is continuous, then we know that these three things, sorry, I should actually have written f of 1 first, but anyway. Okay, we know that those three values should be equal. Now guys, it doesn't really matter what you are choosing now because yeah, they will all be equal. If we're looking at the limit of f of x as x tends to 1 from the left, it's this, hey? All right, so that will be 1 squared plus 3 times 1, which is what? What's 1 squared plus 3 times 1? 4 plus a. Yes? Okay, 4 plus a. And what is the limit from the right? 5 times 1 plus 2. 7. Do we even need to do f of 1? No, because we already have an equation that we can solve. And now from here, it's very easy. We're just going to move the 4 over. Right. Now you're going to practice some of these now, right? Where the information given is a bit different. But guys, it basically comes down to if they're telling you that a function is differentiable, you're going to have to use these two almost like rules. Okay, and sub various things in, it depends on what they've given you, and then solve your equations. Okay. So your homework is here we go, exercise 16.2 on page 182, numbers 1 to 4. There are many, many questions, all right? So you are more than welcome to work through some more of them if you want. And I do have all the answers in the answer book, so even if I'm not doing it, then I can still